Okay, great. Let's start. Welcome everyone to the session on small signal stability. We have 4 talks in this session. Each talk will be about 15 minutes presentation and then 5 minutes Q&A, and then we have a bit of a changeover. So roughly around 2 minutes before the 15-minute mark, I would just say quietly, but I do just say it 2 minutes. So that everyone knows. And the speaker doesn't need to look at the chat to see if I type. And then when time is up, I will signal that we will have the Q&A. Okay, no question. And also for the audience, I believe you can, if you want to ask questions, you can do it on Q&A. And after the 15-minute presentation, we'll go through the questions. I can either ask for you or the co-host can mute and you can answer. Okay, so assuming there's no question, then we will start with the first talk. And we will, unless there's really special occasions, that we will just leave for Q&A questions at the end. So the first talk is by Sultan Alghamdi. The title is Why Oscillation Damping in Low Inertia Time Varying Grid. Sultan received his PhD in EE from University of Leeds in UK this year. Congratulations. And his interest in distributed control and time delay systems. Sultan, please.
Thank you for the nice introduction. The title of my presentation is Wide Area Oscillation Damping in Low Inertia Grids Under Time Varying Communication Delays. My name is Sultan, and I'm from University of Leeds. This is a joint work with Uros and Ognjen and Prof. Gabriela from ETH Zurich and Dr. Johannes from Baden-Württemberg University of Technology and Dr. Petros Aristidou from University of Leeds. I will start my presentation with motivation. Electrical power systems are frequently subjected to low-frequency inter-area oscillations. Insufficient damping of such oscillations can lead to increased losses, excessive strain on generators, and in extreme cases, instability. Underdamped oscillations have been traditionally tackled by deploying power system stabilizers that adjust the power supply for individual generator based on the local frequency measurement. And these are a decentralized controller. Even when decentralized controller provides stability, they may be inadequate for providing sufficient damping for inter-area modes, or even worsen the performance of overall system. In principle, this can be solved by wide area controllers. In comparison to the local controller, the wide area using the communication technology to make use of remote signals, but they may suffer from additional vulnerabilities, one of the most prominent being communication delays. The presence of communication delays influence the system performance and even can be a source of instability. Taking such delays into account is necessary in order to design a well-functional wide area controller. Through my presentation, I will go through 4 main points until we get to the point where I propose a delay robust wide area control synthesis. I will start with the power system model, then move into linearized and reduced order multi-input, multi-output linear system. Then I will look for the controller with considering the communication delays until we get to the closed loop system. Then we're looking for the control design approach using the augmented Lyapunov-Karasovsky functional and the descriptor method and the change of variables. So first, starting with power system modeling. In low inertia systems, the main component contributing to the dynamics of the system are the synchronous generators and the converter base unit. In this work, we're considering the AVR, the BSS, and turbine governor dynamics and the swing equation and the flux leakage dynamics in here. For the converter base unit, we'll be looking for the outer control loop for active power control and reactive power control, and for the inner control loop for the cascaded voltage and current control. Combine the transmission network dynamics with the individual generator units, we can complete set of ordinary differential equations. In this work, for the sake of designing the controller, will be used a reduced order model. So we'll be moving to the next stage, where the dynamical system experience a wide range of a time constant, which increase the model complexity. So this difficult be resolved by employing model order reduction based on the first order singular perturbation. This will lead us to the reduced order model for the linear multi-input, multi-output linear system, as you can see in here. For this system, we want to design a wide area control to damp the low frequency oscillation. So in this work, we'll be looking for a static output feedback controller. This is a simpler and easier for practical implementation than full state feedback controller, since it only required the system output to be measured. In this case, we were looking for the frequency. So moving to the third stage, where we have we put the controller and consider the communication delay together, so we can obtain the closed loop system, as you can see here. So in here, the information follow over the communication links from the ith node to the wide area monitoring and control center, and vice versa, is affected by communication interval delay, where here the H1 is the and H2 is the maximum allowable delay. And also the output performance matrix CZ here is defined such as the output represent the generator frequencies. So minimizing the L2 gain should reduce the frequency oscillation in the system following the disturbance W. And just to recall that the L2 gain is the maximum energy amplification ratio between the energy of the input disturbances and energy of the output of the system. So this is bring us to the objective or the problem statement, where we are giving the minimum and the maximum delays. We want to design a static output feedback controller gain K such that the origin is a uniformly symptotically stable equilibrium point, and the system L2 gain is minimized to ensure damping the low frequency oscillation. So this is bring us to our contribution in this paper, which is we wanted to propose a design procedure for a delay robust wide area output feedback controller to enhance the oscillation damping in low inertia system. This controller can regulate both conventional synchronous generator or converter-based generators. This controller can improve damping of low inertia modes by minimizing the upper bound of the L2 gain. We also will formulate the control design as a convex optimization problem with the LMI constraints using Lyapunov-Krasovsky and the descriptor method. Moving from here, we can go to the main result, where we fix the minimum and the maximum delays. Then for the following optimization problem with the LMI constraint that can be easily and efficiently solved. And for this one, I'm not going to go in details for the mathematics. If you are interested, you can just read the paper. So if this optimization problem is feasible, then for all the delays belong to this interval, the origin is a uniformly asymptotically stable equilibrium point of the power system model, and the system has L2 gain less than a certain gamma. So to validate this proposed control design, we're using a modified Condor 2 area systems, where here we're going to consider three cases. In the first one, we'll consider we having a synchronous generator at all the areas, And the system exhibits 3 low frequency modes, 2 local modes, and 1 inter-area mode. And the second case, we consider in each area, we have 1 synchronous generator and 1 converter-based unit. And the system exhibits 1 inter-area mode. In the third case, we will be considering 1 area with the synchronous generators and the other area with the converter-based generation units. And in that case, the system only exhibits a local modes in here. So to see the performance of the controller, we can see here in the first case, for which is a traditional system with asynchronous generators, the proposed wide area control reduced the system upper bound L2 gain from 2.2078 to 1.3425 and dump out the oscillation, as you can see in here, and while ensuring the robustness against the communication delays in this interval. Also, in the second case, the proposed wide area control also reduced the upper bound L2 gain from 3.019 to 1.7963, and also, as you can see here, damping the oscillation, and also while ensuring the robustness against communication delays belong to this interval. In the third case, we only have a local oscillation. However, the controller can dump out the oscillation, as you can see here, by means of reducing the upper bound L2 gain from 2.0628 to 1.0695. So, for the conclusion, low inertia grids still show inter-area oscillation with the less PSS to provide damping. And the wide area control can help to elevate the problem by coordinating the synchronous generator and converter-based generating controls, but communication delays can destabilize the system. The proposed methodology, we propose a methodology to design a static output feedback wide area controller that showed a great performance of damping the low frequency oscillation with considering the communication delays. For the future work, we are looking to introduce a sparsely promoting feature in the control design to reduce the required information exchange for the wide area control. And also we want to explore further application for time delay stability analysis and control in power system. Thank you for your attention. And just let me know if you have any question. Thank you.
Great. Thank you very much. So there are a few questions in the Q&A. So I'm doing the first time. Let me see if I could just hit, you would like to answer this question live. Okay. They must use Q&A only. Okay. So the co-host, do I read out? They cannot ask live. I have to read their question. Is that right? Yes, okay, sure. Okay, so the first question from Zhao Yuan is that what is the acceptable communication delay for WAG now? Is there any IEEE standard?
To be honest, I'm not aware of any IEEE standard right now, but in any case, even if you have like a larger delay or less delay, you can redesign your controller so you can be able to be robust against this kind of delays. So the proposed design I gave, it allows you to give a range of the delay. Then it's going to be, if you solve the fuzzy problem, then you can get a gain, a controller gain that can be, can make the system robust against this kind of delay.
I see. Okay, great. The next question is also by Zhao Yan. How would the accuracy of the model reduction affect the result? Is the lower order model sufficient to capture the full dynamics?
The techniques we're using here, we're using the first order single perturbation here, which showed that it could capture, let's say, the dynamic of the system. But If you mean, if you're asking about the technology we are, sorry, the technique we are using, it shows a good, result.
Great. Okay. So, is it possible to prove anything analytical about that?
This goes out of scope for paper, but there is another paper for one of the author, Uros, that shows that this technique is a capture good.
Great. Thank you. Okay. So the next question is by Brian Parmentier. Can you clarify how the allowed delay range is computed?
So in our case, we assumed the range of the delay just to show that the proposed control is working, but this can be taken from the operator of the network, from the communication side, because they usually have the data, so you can ask them to give you.
Okay, great. The next one is by Andrei Globunov. Why in the case of converters, there's only one local mode? Is it a dominant mode?
So the reason is the inter-area oscillation coming from the group of the generator with the router, they oscillate against each other. But in the case of you have on one side only converter, you don't have the router because it's only like electronic based. So that why you don't see the inter-area oscillation. However, we saw the local oscillation between the two generators in one area.
Right. Okay, great. So the next question is Francisco Escobar. For simulation purposes, what are the criteria for choosing the delay? For example, should they be chosen? Go ahead.
Yeah, so as I said previously, what we did in our paper, we assumed the interval delay to be able to verify the proposed design, for proposed control design. So, I mean, if you're looking for like using like specific data or like real time, you can just take the interval delay and use the same control design. You will get like a proper control again.
Okay, great. So next question is by Patrick Pensatisi. Do you need to have a minimal phase assumption?
Mainly, if you mean for the power flow, you need to have the security, the phase. It shouldn't be like belong in the less or equal to the pi over 2, if that's what you mean.
Is there a way to clarify, Patrick? I guess we cannot unmute you. Maybe he's typing to clarify his question. But you don't need, I guess if you don't have minimal phase in the undelay. So I guess the one issue is how would the delay affect the minimal phase? So in the undelayed case on linear systems, so we sort of understand, oh, okay, no, it's different. Okay, let's move on. So the next question is from Joachim Burke. What distribution do you assume that the variable delays have?
So again, in this case, we assume like we have an interval delay, okay? So if the delay is belonging to this interval between the minimum or the maximum, the system will be always asymptotically stable.
Okay, great. So the next question is Oscar Kansakinti. In your model, are you using an analytical definition for the delay, or is it represented by a transfer function?
I mean, in my work, we're looking for the time domain analysis. So we're not working with the transfer function, or we're considering like a time varying communication delays. I think if you want to go and use the transfer function, you need to assume only a constant delay. But in my work, we are working in the time domain analysis. That's why we are using Lyapunov-Krasovsky functional.
Right, but I guess there's a critical assumption that the delay lies within bounds that's known, H1, H2.
Yeah.
So the results will be in terms of H1, H2.
Yeah,
Is
so
that right?
H1 and H2 is like the interval that delay belong to it.
That's right. So you know a constant bound. Okay, the last question, also by Andrei Gorbunov. Are the converters grid forming? If it is, what kind of control do you consider? Like frequency drop, voltage drop, a droop, or frequency droop?
Yeah, so it's a grid forming converter, yes. And we are considering for the active power control, we are considering a droop frequency control, yes. But I think you can see in the reference there is like a full detailed of the converter dynamics. But yes, we're using the grid forming, and we're using for the active power control, we're using the droop control.
Okay, so I just received Patrick's clarification, maybe in the last minute. So Patrick asked, when you want to design robust control like H infinity, if the open loop system is not minimal, then it's much more complex. Is that the same in your case?
Yeah, so we're using the L2 gain, which is in the linear system, it's almost the same with the H infinity. Okay. So, yes.
Okay, great. Well, thank you all. Thank you, the speaker, and thank you all the questions.
Yeah.